I'm going to talk about Canadian Electrical Code, Section 26, installation of electrical equipment. Not a very hard section of the Canadian Electrical Code, but a little part of it is difficult, and that's transformers, and it's the sizing of the overcurrent protection. Look at my other video for what the overcurrent protection means, where it needs to be placed, and why we need to place that overcurrent protection. You also really need to know about S, which is apparent power. You also should know what active power is and reactive power before you really understand what you're doing in these calculations that I think are a little bit difficult in this section of the Canadian Electrical Code, which is why I'm making this video just to clarify it. So this is active power and this is reactive power. These are all like power factor calculations or power quality. If you don't know these topics, then put a comment below and I can make you some videos on these topics if you want. It's nice to know your apparent power calculations because those are what you actually have to use in these rules 26, 250, 252, and 254 of section 26 of the electrical code. And if you're being tested on this, it's very hard to work out these calculations. And I hope to make it very clear in this video. You also should know what the voltages are, VL, what the voltage is, VL, which is line voltage, and you should know what line current means because I'm going to use them in this video as I try to simplify these equations for you. So line voltage and line current. If you don't know these things ahead, of course, just shoot me a line down below. I'm happy to make videos about them for you. So what we have to do in these sections, 250, 252, and 254, is we have to calculate the fuses and the breakers that are going to go before the transformer. So we're going to say what has to be in this box as overcurrent protection before on the primary side of this transformer, so that I can take it out of its circuit if I need to. In order to be able to do this, here's what you have to do. Let me summarize all of the calculations for you. I would say that in order to size transformer equipment according to rules 26, 250, 252, and 254, you really have to organize yourself. So let's organize our calculations in this table. I would say the first thing you have to do is calculate. You have to calculate the the current. You have to calculate the line current in the primary windings and in the secondary windings. Now, the thing that makes this section difficult is just that it's hard to organize kind of in your brain because you have a few situations. You have single phase, and we call that 1 with a phi there. And then we have 3 phase. And we calculate apparent power a little bit different in single phase and in 3 phase. Same with secondary windings. We do it the same way. Single phase. 3 phase. And 3 phase. Now we're a little bit more organized in these sections of the code. Now, how do we calculate apparent power? Again, if we don't know this and we don't know anything about transformers, then I feel like this would be a really difficult section of the Canadian Electrical Code. Let's simplify it a little bit for you. The formula that you need to know is that apparent power in a single phase circuit is equal to voltage. Power is voltage times current, right? But in this case, we're just getting a little bit more specific about what kind of power. The apparent power, which is S, in a single phase circuit is simply equal to the line voltage times the line current. Now you know. I don't know how you do this section without knowing that. And if you want to know why, then of course you need to know why, and you need to look up you need to look up power factor and power quality calculations. But in a three-phase, it is square root of 3 times voltage of line, current of line. And in your code, you do see that. But in the code book, the Canadian Electrical Code Book, Part 1, 2018, well, all of them, it just says 1.73. So just note here that 1.73 actually comes from square root of 3. And the square root of 3 actually comes literally from the geometry of a three-phase system, which if you don't know about, I can explain where that root 3 comes from. Just fire me a note below. Okay, so those are the formulas that you have to use. Who knew that? If you didn't know that, you're kind of in trouble. And what you have to do then for the primary windings is you're going to rearrange this equation. So all you have to do is say I line, you have to solve for I. I line is then going to be equal to the apparent power, single phase apparent power over voltage, over the line voltage. That's your formula you have to use. Your line current, or the current in your primary windings, if it's three-phase, is going to be the apparent power in your three-phase circuit divided by root 3 line voltage. That's the equation that the Canadian Electrical Code is using in their first step of transformer sizing. That's it. That's the secret that you're missing. Now, why is there a 1000 in there and why is there a 1.73? Well, the 1.73 is the square root of 3. It came from geometry. It's only in the three-phase questions. If you're answering on your test a one-phase question, don't put in root 3. If it's three-phase, then you use the root 3. And there's a very, very good reason for that. Now, what is this going to look like to you when you're doing the equation is that you're probably going to get your question in kilovolt amps. And this equation only works in volt amps. All right. In order for this to come out as amps, then you have to be in volt amps. S is in volt amps in this equation. Oops, it's in volt amps. So that's important. If you have a kilovolt amps going in and your parent power calculation or your formula is in volt amps, then that's why the Canadian Electrical Code has that 1000 in there. It's just to do that conversion. So here's what the formula actually looks like to you when you are using it for your test. It's going to look like you want your current. You want the current of your primary windings. You want them to be in amps. So that's going to look like the S that you're given in the question, which is going to be in kilovolt amps. And then you're going to want that to be in volt amps. So you would have to recognize that there are 1000. Let's see if I can do this a little bit thinner here. You would have to recognize that there's a ratio of 1000 volt amps in 1 kilovolt amp. That's where the 1000 comes from. And then you would also have to divide by VL, because I said that's on the denominator. So let me just do that over here. 1 over VL is the same as dividing by VL, and that is in volts. All right. So that's why this is the formula that you see in the Canadian Electrical Code, and you should be able to recognize this at this point. And let's look at that. If it is a three-phase primary winding you want to calculate, then it is going to look like S, which is three-phase, which is typically given to you in these calculations. Recognizing that they give it to you in kilovolt amps means that you want to be able to cross these kilovolt amps out. So I want only volt amps in the numerator. I want to cross out kilovolt amps. If I'm going to cross out these units, I have to have the ratio of 1000 volt amps in 1 kilovolt amp because kilo means 1,000. I also need to divide by VL. So 1 over VL is how I'm going to show that in my math, and that's in volts. And I need to divide by √3. So I'm going to multiply by 1 over √3. And in your Canadian electrical code, you'll just see divided by primary line to line volts times 0.13. So I'm just showing you how to do that math in a little bit of a more clear way. If I think about this as a ratio, I'm multiplying S, I'm converting the units, I'm dividing by voltage, and I'm dividing by √3. So that's how I would approach this, these primary winding calculations, which are the first step to sizing your transformer equipment. Now, what about the secondary windings? Guess what? Secondary windings are exactly the same. So you're going to use the same calculation. You're going to use S primary winding, S single phase, S three phase, apparent power. That apparent power is going to be in volt amps. You are going, it's just voltage in volts times current. These are line voltage, line current in amps. Same equation as before. For three phase, you have that √3. There are good reasons for that. If you don't know the reasons, comment below. I will make you a video about it because you ought to know. Times voltage times current, because that's how we calculate power. These are line voltage, line current, same equation as above. Then you're going to rearrange that equation in terms of I, line current, same as you did above. So it's going to look like this. It's going to look like this, exactly the same. Let's do the answer, what it ends up looking like to you, so that you can recognize what they were doing in the Canadian Electrical Code when they do sort of an example like this. Then what that looks like to you when you're calculating it, you want that line current of the secondary windings. In this case, for three phase, you also want the same thing. When it is single phase, I am given the apparent power in single phase. In three phase, I am given the apparent power of a three phase. They are typically given to us in kilovolt amps when we are tested on this, because that's practical. Kilovolt amps, because it is sort of used, these high voltage transformers are used for power systems. Transmission and distribution tend to be over 750 watts or thereabout. Therefore, kilovolt amps is sort of the extent of like the magnitude of the power that we're dealing with. However, we don't like kilovolt amps. We don't like kilovolt amps. In either case, we want to cross out the numerator and denominator here. In order to do that, I need to know the ratio to volt amps. I want to keep the unit of volt amps. I have to give myself a conversion of 1,000 volt amps into one of those amps. And then, of course, I need to I need to move my voltage to the other side as well by dividing by voltage, just like I did up here. I'm following this formula right now. I want to divide by the voltage is the same as multiplying by the inverse of the voltage. I'm dividing by the voltage, multiplying by the inverse of the voltage. That's measured in volts. That's measured in volts. And that's it for single phase. And three phase, we don't forget about this √3 that we also have to divide by 1 over √3. And that's how we do it. So this is the line voltage equation for single phase. It's the single phase secondary winding current, and it's a three phase secondary winding current. This was the single phase primary winding current. This is the three phase primary winding current. Those are the first steps to this section of the code where you're going to have to calculate what the current protection device is for a transformer. Now it gets, it's actually pretty easy. I was going to say now it gets complicated, but it's actually pretty easy, because now you either have a high voltage system, which is greater than 700 and 50. Here we go. High voltage or low voltage or dry type, low voltage. So here's high voltage, here's low voltage, and here's dry type, low voltage, -750 dry type. All right. So now we say, okay, well, how do we size the fuse or breaker? That's the point of this section of the code. Well, first I had to calculate these primary, secondary windings. Now I need to organize my thoughts again, or else I fail this part of my whatever test I'm doing. On high voltage, you can use fuses and you can use circuit breakers. You do that calculation differently for fuses and circuit breakers, it makes you sad. Okay, that's how it's confusing. In low voltage, you do the same calculation. Fuses or circuit breakers. And that makes me happy. So to do the calculations for 26,252, it's easier than doing them for 250, okay? But it's not that hard for 250. You just have fuses and circuit breakers, you're doing a different way. All right, so let's look at these, and these are both oil cooled. These are both oil. All right, so let's look at what we do for fuses. Let's get a nice new color and just organize our thoughts. For fuses, all we say is maximum calculated fuse rating is equal to 1.25, 125 times I line, and that's going to be in amps. Well, what's I line? Here's I line, right? And so it is of the primary winding. Primary. I line of primary. Of the primary winding. And then for the circuit breakers, same thing. Max calculated circuit breaker rating is equal to something times I line of primary, which I calculated above, I line of primary, time, and that's all going to be in amps. Well, the only difference is that this is 300 times. If you're using a circuit breaker, you have to be 300 times that current. If you're using a fuse, then you only have to be 125% that current. That's it. But wait, there's more. You're all saying, oh my goodness, I don't know when to round up. I don't know when to round down. Well, to get to the standard, here's the part that's confusing in the code. Here's the part that's confusing. Round up or down? This is what you don't know. Round up or down. Because a circuit breaker is not made in like, I don't know, what are you gonna get? Like, 152 amps. A circuit breaker is not made in that. Circuit breakers are made in the standard sizes. Standard sizes of the circuit breakers are in table 13 in the tables section of the Canadian Electrical Code. And you see that they go from like 150 amps to 175 amps to, I forget, but what if you get 152? Do you round up or do you round down? And you see a bunch of examples for rounding up, and then you see a bunch of examples for rounding down. Actually, most of the time you see round down, but you know that there is a provision in Rule 26.250 that says that you can round up. So here's the problem. 26.250 provision 2, subsection 2 says you can round up. Cool. So you're going to round down. Usually, you're going to round down. And here you're going to round down. Usually, because it's better to have more protection, it's better to round down. So if you get like 755, you're going to go 750, usually. But provision, subsection 2 says that if you chose a fuse only, if it is high voltage only, if it is oil cooled only, and this is a big power system distribution transformer example, you can actually or round up, but be very careful when you round up. In this case, you can, yes, round up. Why would you want to round up? Round up if you're going to nuisance trip. If you have a special case where it is safe to round up. If you have to round up. But usually you'll round down. Can you ever round up a circuit breaker in this high voltage application? Never round up. You can only round down. And where is the rounding? The rounding is found in table 13. So this answers your question about why do I see all these example problems where they round down when provision 26250 subsection 2 says, hey, you can round up if it's a fuse in high voltage. Well, now you know. It's because that provision has to be there for some cases, but usually you will round down. When you're in the industry, you will know, your trade knowledge will tell you when you would actually use that rare subsection and round up. Now, sometimes you have a low voltage, but still oil cooled. What do we do in that case? Well, for fuses and breakers, we do the same thing, except we go greater than or equal to 9 amps in the primary winding is one case, and less than 9 amps in primary winding is another case, and less than 2 amps in primary winding is another case. So this one is a little bit of a pain as well because it depends on how many amps are in the primary winding. And if there are a lot of amps in your primary winding, then your max calculated circuit breaker or fuse will be 150 times, so 1.5 IL primary in amps. If it is less than 9 amps, then your max calculated protection will be equal to 1.67 times IL primary in amps. And if it's really low current, then your maximum has to be 300, which is going to be 3.0 on your calculations, times IL primary, which we calculated above in amps. So 1, 2, 3 calculations we have now organized for any low voltage, less than 750 volts cooled. Sorry, not air, not dry, wet, or oil cooled. That's for fuses and for circuit breakers. And what do you do? Round down. You round down. There's no other provisions for ever rounding up. Round down to table 13 in the table section. I don't know why that does that, but round down in the table 13. Okay, so those are the calculations you do. The same calculations, all we're doing is changing that factor that you're multiplying by. For all low voltage dry, our max current or our max circuit breaker or our max protection, I'll say fuse or circuit breaker, is going to be equal to 1.25. It's 125% times I line primary, which will be measured in amps. Everything. So how do I say everything on this video? I don't know. I'll say fuses and circuit breakers, all current. Just everything. And then, of course, in orange, I'm going to say round down table 13. Okay, because you can't buy, like probably what you're going to get there. Now, the minimum for everything is also mentioned in the Canadian Electrical Code. That's what 26256 says, is that max protection must be at a minimum 1.25 or 125% of the primary current that you've calculated in amps. And guess what you round? You round up or you round down? You would round down. So I hope that has served as a nice sort of cheat sheet for you for the sizing of transformer equipment as it pertains to section or to rules 26.250, 26.252, and 26.254, why we sometimes round up, why we sometimes round down. And I just want to highlight for you so that you feel extra comfortable about this. All this was about is these factors. These sections just give you these factors of 150, 167, 300, 125, 300, 125, and 125. That's all it's giving you, but it is incredibly confusing. When do we use each of these factors? And when do we round up in table 13? And when do we round down? The answer is you only round up if it's a fuse in high voltage, but usually you round down. Sometimes you need the provision to round up. That's why it's written into the code. And also as a summary, how do you do these calculations? Step one is to calculate the primary current or the primary winding line current. And then step two is all of this, where you're going to be calculating the maximum fuse or circuit breaker according to these ratios. I see this as a nice cheat sheet for trying out these calculations. If you want to see me try out some of these calculations based on this cheat sheet, then let's watch the next video where I go through a bunch of examples using these calculations. Hope that was helpful. Feel free to comment below. Thank you.